All right, hello, welcome back, College Chemistry. We are going to start semester 2 with gases. Gases is really typically unit 5. A lot of times we cover that before Christmas break, but we decided this year to go a little different order. So here's what I'm going to do. I'm going to kind of give you a quick overview of states of matter. I do think this would be smart if you wrote some things down here. And so I would grab a piece of paper and a pencil and come back and join me when you do. All right, I'm going to click on states of matter here. And I just want to talk through a little bit of kind of viewing things at the particle level. If you look closely here, this is supposed to represent solid neon. Notice my temperature, 14 Kelvin. It's actually really cold. If you wanted to take neon gas and turn it into a solid, you'd have to make it really cold. Okay. So if you look closely here, if you were to describe what do these particles look like, how are they arranged, you would say that they are tightly packed and they're kind of clumped together. Okay. And yes, they're still moving a little bit because anything that has above 0 Kelvin temperature has motion to the particles, but they kind of move together. That's what solids look like. There's a lot of interaction, a lot of attractive forces that are kind of holding them together. If you were to heat this up enough, you're going to see that you're going to break some of those attractions and we're going to turn things into a liquid. Notice liquid particles are still very close to each other and touching. They just have a little bit more freedom to slide past one another. So actually liquids are pretty similar to solids. They've just lost a little bit of that structure because you've overcome some of those attractive forces. But if you look closely, if I were to keep heating this up and I were to turn this into a gas, by continuing to heat it up, here's what you're going to notice. Let me click on gas. You're going to notice that these particles, they kind of act independent of one another. They just bump into each other. Yeah, some of these, like these two here, they're kind of still attracted. But for the most part, gas particles really don't have these attractive forces anymore. We will kind of assume that there's no attraction between forces. Later in the unit, we will kind of talk about reality of kind of assuming or talking about what those attractive forces would look like. But I want you to kind of have this visual and I want you to think about how would you describe gases as far as looking at these particles here, okay? Some things that probably keep, you kind of look at and you say, how would you describe the motion of these particles? Well, first of all, gas particles are in constant motion, right? So what I'm going to do, I'm going to kind of bounce back and forth here. I've got, if I can find it, I've got a little note section here for you. Here we go. When we get into what's called the kinetic molecular theory of gases, there's really 5 big assumptions that we say about gases. And this might be a review from last year or first year chemistry. This is great if it is, but I want to hit these again. We say that gas particles are in constant random motion. And again, if you go back to our, where is there we go. I'm going to move this over by my notes. They're in constant random motion, right? They just move in a straight line until bang, they hit something. So that is one of the assumptions that we make. Gas particles are in constant random motion. The other thing we assume about gas is that most of a gas is empty space. So if you look closely at wrong one. If you look closely at the container here, most of that gas is an empty space. Now, if we went really technical on this, these gas particles are way bigger, relatively speaking, than they should be. But if you went with the size they should be relative to the space, you wouldn't be able to see those particles very well, and it would be hard to kind of visualize the gas. So this is even way bigger particle-wise than you would expect. But most of this is empty space. And therefore, because of that, the gas particle's volume is so small, we kind of assume that gases don't have volume. Okay, most of the gas is empty space. The volume of the gas in itself is insignificant, so we just round it to 0. We also say that there's no attraction between particles. When we get into reality, real gases later in the unit, we'll talk about some of those attractive forces. But the idea is because these are so far apart and just bouncing off each other, that we really don't have a lot of attractive forces. And that's kind of one of the assumptions that we make, okay? Collisions are perfectly elastic. What does that mean? We'll go back and look at our picture here. When they bounce off each other, they don't lose or gain any energy overall. They basically just transfer their energy from one particle to another. So there's no loss in energy They are perfectly elastic, perfectly bounce off each other as they do that. The next thing we would say is, and the fifth assumption is, the temperature of a gas is actually a measure of its average kinetic energy. Okay. So when we get into, and we'll get into that a little bit later in the unit, we're going to actually calculate or show the equation how to calculate the kinetic energy. And if you've had some physics, maybe you've already talked about how to calculate kinetic energy of an object or a substance. We'll kind of get into that. It does kind of involve the mass and the speed or velocity of the substance. But what we're looking at here is when we talk about temperature, in fact, if I heat this up, what does this do to the gas? Well, it actually speeds up the particle. So if I add heat, I'm really increasing the kinetic energy, and it makes these particles move faster and faster and faster. If I cool it down, okay, it actually slows down the particles. It slows down their motion. So when we talk about this temperature here, the temperature is actually a measure of the average kinetic energy of a substance, okay? All right, so that is the 5 assumptions, the kinetic molecular theory of gases. You need to know those, so I would make sure you have those written down. The other thing I want to talk about, and this is going to kind of lead us into what we're going to do kind of moving forward from here. But there's 4 real important properties that you need to understand about gases. And when you think of a gas, probably one of the best things to do is picture a balloon. And it's kind of hard to kind of picture at the particle level, the balloon. But again, I would picture something like this. These particles are in constant random motion, these assumptions we've been talking about. But gases are easy to compress, okay? And when we say they're easy to compress, let me see if I can pull up, a different simulation. That's not what I want. Let me go back and let me pull up the simulation with, let's go with intro to gases. Gases intro, okay? When we talk about the properties of gases, some of the things we can talk about here is we can say that, let me pump some air, put some gas particles in our container. What can we do with gases? Because there's a lot of space in between the particles, we can actually compress them. We can squish them closer. So what I'm going to do is I'm going to shorten or get my container to be smaller, right? Shrink it in size. And so we can actually compress gases. And if we compress them enough, we can actually get them to go back to a liquid. And we might show you some visuals of this in class, but we can also, expand the volume, et cetera, and give them more space. But one of the things that's true, because there's a lot of space between the gas particles, is gases are actually easy to compress. There's a lot of space that they take up. In fact, the second property of gases I think you should know is that gases expand to fill their containers. And you can kind of see that here. If I just open my container bigger, the gas particles just continue to spread out. If you give it a small space, it'll take up the small space. If you give it a big room, it'll take up a big room. So whatever the amount of space you give a gas, it will take it up. Okay. Gases have low densities. Okay. What do we mean by that? When we talk about the mass to volume ratio, if we were to take all of these particles and shove them in a corner and find the mass of those particles, the mass is going to be pretty small compared to the amount of space this gas is taking up. And so densities with gases, instead of typically going with grams per milliliter or grams per cubic centimeter, we do with liquids and solids, we actually tend to go with grams per liter with gases because they have such low densities, okay? The fourth thing about this is gas exerts pressure. One of the other properties you need to understand is that when gas particles are bumping and running into things, they put pressure on their substance, on the container that they're in. And so these bounce off of each other, yes, but they also put pressure on the container. And so one of the properties that we will look at is pressure of gases, okay? Now, in terms of those are the 4 properties we really want you to know. And we get into gases, there really are 4 variables, and they kind of all connect to what we just talked about here. There's really 4 variables that we will measure or do stuff with in this unit is pressure, volume, temperature, and number of moles. So I'm going to have you write those down: the pressure, the volume, the temperature, the number of moles. And then I'm going to go back to our little simulation here. And I want you to look at all of these things are kind of connected to each other. I'm going to switch to this mode here, and I'm going to put some particles in. This right here, when I add more particles, this is actually related to the number of moles of a substance. So if I want to increase the number of moles of a gas, what do? I just add more particles of the gas, right? And the number of moles do affect things going on in the gas. If you notice here that as I add more particles, it actually seems to affect the pressure of the gas, right? Which makes sense. There's more collisions, there's more pressure. If I decide to change my volume, that's one of the variables, right? If I expand my volume, since it gives the gas more space, you're going to have less often collisions or pressure changes. The temperature, if I heat up the gas, for instance, so if I can increase my temperature, notice my pressure is rising right now. So there's a connection here, and we're going to talk about that in one of the next videos. These are really the 4 variables that we will deal with: is pressure, temperature, volume, and number of moles when we deal with gases.